Swayam Prabha. Digital India. Educated India.
So let us start the class today. Basically, first let me just take 5 minutes to recap what we did in the last class. We said that when we go from single degree of freedom system to multi-degree of freedom system, okay. Usually, multi-degree of freedom system is a better representation of the systems that you would be dealing in real life. But for some of the problems, single degree of freedom system is just easy to deal with. We have standard analytical solutions. Okay. But in the end, if we want accurate solution and if we want for certain kind of a structure, we'll have to resort to multi-degree of freedom system. Okay. Now we'll have to make that transition because any system is basically a continuous system. Okay. And in general, a continuous system would have infinite degrees of freedom. However, till now what we have done, we have only represented is using a single degree of freedom system, but later we'll have to consider cases in which it might be represented as multi-degree of freedom system. Okay. And then we said that before going into this multi-degree of freedom system, okay, so these are the two representation. Is there a way through which we can analyze a continuous system without having to deal with multi-degrees of freedom? Okay, and for that what we did, we defined generalized SDOF system. Okay. In a generalized SDOF system, we basically said that if we have any structure, okay, we took a very simple example of, let us say, simply supported beam or a cantilever beam. Okay. And if it is deflecting, then initially for a single degree of freedom system, only the location at which the degree of freedom was defined was important. Okay, so if you remember, whether it is a spring mass damper system, as long as you were able to find out what is the deformation at this point, okay, it was sufficient. However, for a continuous system, okay, at different time, okay, the deflection would look like something like this for a simply supported beam and for a cantilever beam. So we said that at different locations in the structure for a continuous body will have different deformation. Okay. And that deformation, let us say it is at any coordinate or any distance x, okay, which is measured according to this coordinate system. Okay, and we define that, let us say at any time t, the total deformation is ux, because now the deformation at this point or a different point would be different. Okay, so it would be ux here, and let us say in this case here again it is ux t. Okay, so the total deformation would be a function of the location x, and it would also be changing with time. Okay, because it is being excited by, let us say, some external force. Now we said that we can decompose this function uxt as a function which is phi x times zt, where phi x is basically the shape function of deflection and zt is the time variation of deflection. The physical significance of that is, if you consider a constraint structure like this, okay, let us say it is constrained at these ports and this kind of position points on the body, and that does not change. So, and we try to explain it in terms of shape and size, that whether it is this or whether it is this or whether it is this, the shape is not changing as long as the aspect ratio of the sides remains same. However, the size is changing. Okay. So what happens with time, it is increasing from this small size to this size to this size. So one aspect is the time variation, which is increasing. The second is the, if I represent the position like in the two-dimensional, it would be a phi xy to represent the relative location of any point on this structure. Similarly, for this one-dimensional structure, single degree of freedom structure, we defined this phi x, which is a shape function which basically represents the relative position of different points on this structure. Okay, and I gave you some example. For example, in this cantilever beam, we said that it could be represented as parabolic shape. Okay, remember all these are approximations. Okay, or it can be represented as any other function. Let us say cos pi x by 2l or any other shape function. The precondition was that this shape function must satisfy the displacement boundary condition. And what are displacement boundary condition? For example, if you want to represent the deflected shape of the simply supported beam or this cantilever beam, as long as your shape function is consistent that for the simply supported beam, the deformation is 0 at x equal to 0 and x equal to the total length of this simply supported beam. Okay, so in this case, it would be phi 0 and phi L. These should be equal to 0. For cantilever beam, basically at 0 it is equal to 0, and the slope, because it is also fixed at the other this left end, it should be also equal to 0. So you can assume different type of shape function. Okay, and that can be used to reduce this continuous system to a single degree of freedom system. Okay, as long as it satisfies the displacement boundary condition. So finding out the shape function was one of the important tasks. Okay, so the shape function represents the basically relative location of any point. Now, if you are also able to find out what is zt, which basically represents the time variation of the deflection, okay, how the it is changing with time, then you can find out at every location at or at any time what is the, sorry, not phi x, but what is the total deformation by multiplying phi x with ut. Okay, and we tried to derive the equation of motion for continuous system using principle of virtual work, where we said that external work done is equal to internal work done. Okay, and using that, we found out that equation of motion basically comes out to be in this form: m equivalent times z double dot t plus k equivalent times zt, and this is equal to some parameter which is called L equivalent times ugt. Now note that this is for condition where we are considering excitation as a form of ground excitation. Okay, now these we derived where m equivalent we found out as, okay, so the important thing to remember here is this expression that we derived. Okay, this is integrated over the whole length, whatever the mass variation of the continuous system is times the shape function that you are assuming. Okay, integrated over the whole length, and k equivalent is the flexure rigidity. Okay, EIX times the phi a double dash x square dx, again integrated over the whole length, and L equivalent is basically mx times phi x dx integrated over the whole length. So this is what we derived. Okay, the three expressions, right? So once we have that, this is the system. Okay, is the familiar form of the equation of motion that we have been dealing so far now. Okay, and we know that once we have obtained m equivalent or k equivalent, it is quite easy to find out the frequency. Okay, which would be k equivalent times m equivalent. So the frequency square would be this. Okay, and you can substitute the expressions that we have to find out the frequency of the system. Okay. Now, remember that this equation that we have derived, okay, this equation of motion, this was without damping. Now we don't have a similar formula for C equivalent here. Okay, because typically what happens, as we have previously said, the damping for a structure is not determined from the structural properties, isn't it? We never said that it would be determined from the shape function or whatever the m is, mass variation or whatever the stiffness variation is, typically what happens, we assume some damping for a structure which are typically determined from experimentally using what? Using the methods that we have previously described, logarithmic, okay, logarithmic decrement method or half power bandwidth method. Okay, so those are determined experimentally, not your job. You would be given typically what is the value of damping if you need to solve a problem. Okay. So for example, typically what happens, and this is very approximate number, you can, in reality, it would be a little bit different. Steel structure are said to be damping in the range of 2 to 3%. Concrete structure are said to be a range of like, 4 to 5%, like that, so just an approximate value. Okay, so damping is actually given, and then this equation can be written including the effect of damping. Now, if you look at here, if I divide this whole expression, okay, by m equivalent, I can get this as ZT divided by K equivalent times m equivalent, okay, times, and this is equal to, okay, you might already be familiar with this expression. So we are going to write it in this form, first for an undamped system and then for a damped system. And this we are again going to represent with a new parameter called gamma equivalent. Okay, where gamma equivalent is basically L equivalent divided by M equivalent. And if you want to write it in terms of expression, it would be mx phi x dx integrated over the whole length divided by mx phi x square dx. Okay. So if I have a damped system, similarly, I can write this expression as, okay, ZT plus C equivalent, whatever C is defining. Okay, or let us say we are defining it, writing in terms of zeta. I can write this expression as 2 zeta omega n Z dot T plus omega n square ZT. Okay, this is for undamped and this is for damped. Now, once we reach up to this step, the next subsequent steps are familiar to us, isn't it? I mean, once we find this out, we can find out what is the ZT here, what is the peak value of Z. Okay, and then if it is asked to find out peak forces and moment or displacement, we can always find out peak forces. So not T here, just U naught X would be phi x times whatever the value of Z naught here would be. Okay, so that's not a difficult task to do. Whatever, once you find out K equivalent and M equivalent, you have effectively reduced a continuous system to a single degree of freedom system and then solve this equation. Okay, now what happens that here we are doing it and the question might arise, when we are going to solve the multiple degree of freedom system anyway, why do you need to do this? Well, what happens that many times you were told that assume the mass is m by 2 or it is lumped at like or equivalent stiffness is this much. You never knew that how that number was coming from. I mean, whether m by 2 is a good enough approximation or not. Okay, and it becomes important to determine that, because depending upon the boundary condition, you might see that if you consider a cantilever beam, okay, it cannot be simply approximated as a spring with 3 EI by L cube and mass equal to m by 2. If you consider, let us say, tributary mass. Okay, it might be something different. And what is that value? How do we get that? Well, we get that using the method that we have just described here. Okay, and this is the method that we would be following. Okay, any doubt up to this step? Anybody? If not, then let us do an exercise to actually see the significance of this method. Okay, what I need you to do, consider three shape function. I'm giving you three shape function. First shape function is basically represents the static deflected shape of a cantilever beam, okay, under the action of a point load at one of its ends. Okay, and I'll just give you the normalized deflection. So it would be 3 by 2 x square divided by L square. Okay, and then 1 by 2 x cube by L cube. This is first. The second one is cos pi x by 2L. Third one is x square by L square. The first thing to find out when you are using a shape function to see whether it is satisfying the displacement boundary condition or not. And we discussed in the last class that all three functions are actually indeed satisfying the boundary condition. Okay, so using this, okay, and assuming that mass per unit length is m, okay, or let us say that total mass is m, which is mass per unit length times L. Okay, can you find out, and I'll give meters as well. Flexure rigidity is EI, which is constant. Okay, this is for the cantilever beam that I have shown you here. This cantilever beam. Okay, total mass M, flexure rigidity constant EI, length, total length is L. Okay, these three shape functions are there. What I need you to do, find out first M equivalent, then K equivalent, and then frequency for each of these cases. Okay. Use the expression that I've just showed you. Okay, I want these values for this shape function, and then we are going to compare. And then we are going to see how does selecting a shape function affects the overall accuracy of the properties that we are determining here, the modal properties. Okay, omega n and the equivalent properties M equivalent, K equivalent. Okay, so take 10 minutes and try to solve this problem. Use the expressions that we have just derived. Okay, anybody with the answer for all of these? Let us first consider this first case where the shape function basically represents the static deflected shape. Okay, and we are assuming that dynamically also the structure is going to deflect it like that. Okay, that is an approximation. Now we are going to substitute that in the expression for mx or the m equivalent, sorry, here, which would be nothing but 0 to L mx times phi 1x dx. And so I want to do it for all of them. Again, I'm just writing down the expression. You can substitute and integrate it. Shouldn't be very difficult. So the first case, what you are getting as M equivalent, can somebody tell me? I'm getting this as 0.23 M. Is it correct? 0.23 M?
0.257. Yes, sir.
33 by 140.
Yeah. And K equivalent I'm getting as I by L cube. Okay. And if you substitute in the expression for omega n, okay, it would be 3.61, okay, times EI. If you want to write it in terms of mass per unit length, you can take L4. Outside it would become L square like this expression here. Now same thing for this second one. I'm getting as 0.227 M. K equivalent I'm getting as 3.04 times EI by L cube, and omega n if I substitute this, I'm getting as 3.66 divided by L square EI by M. How about for third case, which is easiest in terms of integration? Okay, you are getting as M equivalent. Anybody?
0.2 m. 0.2 m.
0.2 m.
0.2 m, correct. And K equivalent as 3 EI by L cube. We derived this last class, remember? And then substitute it. What do we get here as frequency? It would be what? Can you substitute and find that out for me?
So the K equivalent is 4EI by
Sorry, 4 EI by L cube, correct. This is 4 EI by L cube. Okay. So it would be 4.47 under root EI by M. Okay, now let us go through each of these because it's important to understand what is the repercussions of using a shape function on the overall accuracy. So if you look at these two functions, which are the static deflected shape. Now, if you are selecting a shape function which is the static deflected shape, okay, then it would always satisfy the displacement boundary condition. Why is that? Because if you are taking the same structure and finding out the response due to static load, by default, because it is the same structure, it would have the same boundary condition. Okay, so the boundary condition, the displacement boundary condition would always be satisfied. Okay, so if we look at it, this is even the K equivalent is 3I by L cube, which is same as what we would have derived or considered if we had simply reduced this using our initial methods. Remember, when we apply a cantilever beam, a load to a cantilever beam, okay, a point load at the top, what happens? Basically, the equivalent stiffness we said that was 3I by L cube, which is the same case even if I assume the shape function and derive it. Okay. However, the mass here is now 0.23 m. It is not m by 2. Okay. And look at the frequency. Accordingly, we have calculated this. Now, we are looking at the second shape function. Okay. It is not very different. The mass that I'm calculating, it is not very different from the first shape function. In fact, even the K equivalent is not very different. Okay. And your frequency is also coming out to be almost same. Okay. So these two shape functions are providing very accurate result. Okay. However, look at the third one. Third one is actually the differences increase. Okay. Because I have 0.2 m, 4EI by L cube, and then 4.47. So in terms of deviation, this shape function providing the maximum deviation compared to first two shape function. And this has to do with whether the dynamic deflection is actually close to the static deflection or not, or whatever the shape that you are assuming. If your shape is close to the if your shape function that you have selected is close to the dynamic deflection, these values would come out to be okay, closer to the actual value. The question is, what is the actual value? Well, there is a theory, a beam theory, you can go and you can have a look at it, and there the expressions for the actual values have been derived, where the frequency have been found out as 3.516 EI by M L square. Okay, and this was derived without having to assume a shape function or anything, just solving the overall equation. Okay, and it is given in your textbook as well. If you go to chapter 17, if you are more interested in it, you can go and explore it. Okay, but I'm just giving you, this is the actual value without any approximation. Okay, but to derive this, it was only possible for a simply supported beam. If the situation is more complicated, okay, then deriving this becomes like, very difficult, and also it is not computationally feasible because this one is very easy to determine. Okay, so shape function play a major role on the accuracy of it. Okay, now the reason why this one is providing the maximum error, if you look at it, what you will see, these two are actually all three are consistent with the displacement boundary condition. However, the first two are also satisfying the geometric boundary condition. Okay, what it means, remember, at the free end, can I say, okay, can I say at the free end, if you consider the force or the moment should be equal to 0, isn't it? If I have a beam like this, can I say at the free end moment should be equal to 0? Now we know that the expression for moment is given as what? EI times I double dash x. Okay. Now, if you look at it here, and if you substitute the value of phi dash x, this will have a non-zero value. Okay, because the double differentiation of this would be 2 by L square, and it will have non-zero value. Compared to these, if you substitute, okay, at x equal to L, you will see that phi 1 of basically phi 1 double dash L is equal to 0, phi 2 double dash L equal to 0. However, phi 3 double dash L is not equal to 0. Okay. So while all three satisfy the boundary condition and are appropriate to be used as shape function, the first two are more accurate because they also satisfy the force boundary condition. So this is just for your understanding, although this does not have any direct implication in terms of the problems that we do in this chapter, but just for your information, why some shape functions are more accurate than others. Okay. Typically, what happens, the deflection deformation has to satisfy the displacement as well as the force boundary condition, depending upon whether some satisfy only the selective displacement boundary condition or both, they might provide a better or accurate results. Okay, like we saw in this case. Okay, is this clear to all of you? And I hope now you also understand how the shape function can be used to find out the equivalent properties. Okay, once, any question up to this point? Anyone? Okay, once this is known, the equivalent properties, the natural next step is basically solving this equation of motion for the generalized coordinate, let us say, or instead of writing in an equivalent, let me write it in terms of z double dot t plus 2 zeta omega n zt plus omega n square zt here. And that is equal to gamma. Okay. Now, the next step comes subject to these conditions. How do we find out the forces? Remember, unlike a single degree of freedom system where forces were needed to be found out at a single point, like in case of uh, spring mass system, the forces or the everything moment were needed to be found out at a single point, let us say at the support. This is a continuous system. So we have basically we would have internal forces and moments. We need to find out what are the internal force and moment. So if I consider shear force, it would be again function of x and t, and if I consider moment, again it would be a function of x and t, because for every location we need to find this out. Okay, so to do this, to get this, basically what we need to do, we will utilize the beam theory, one or two formula from beam theory. If you remember, okay, if you have, let us say, a distributed load like this, omega x, okay, do you remember this equation that this applied force is nothing but EI x, okay, times ux, okay, u double dash x basically to the power over Okay. And if EI is constant, basically this becomes EI fourth power to the x, or EI d4u by dx4. Okay. This was the equation you might have seen, and we are going to employ the same thing. Okay. So for a case of an earthquake excitation where we said that we have this, okay, and there is an earthquake excitation here. Okay, that the ground displacement is UGT, and we formed something like this, and we use the virtual displacement to derive the expression. This we considered as U, this as del U. At the end, we normalized with respect to end displacement. So we said that this would be Z and del Z. Okay, the inertial force on this would look like something like this. Here only due to ground motion, but as you go above, it would be due to the relative acceleration plus the ground acceleration. So this I said it is Fi xt. Remember, x is in this direction. Okay, and we are going to use the again same principle, equivalent static force. So we say that I'm going to apply equivalent static force, which is going to produce the same dynamic displacement in the system as what have been obtained from the dynamic analysis. Okay, so I'm going to say I'm going to apply equivalent static force. Okay, and I'm going to denote this equivalent static force as Fs of T. Okay, let us say that this is the equivalent static force I'm talking about. This is my F xt here. Okay, at any distance x. Okay, and I'm saying I'm going to apply this force here. Okay, so that, and I'm going to do the static analysis. So the deformation due to this static force is same as the deformation due to this dynamic force. Okay, and this can be done because we had discussed this concept in the previous chapter. Okay, that if you have a system which is undergoing dynamic response, you can apply a equivalent static force. Okay, that does not have mass in it, and basically do a static analysis and get the same response. So basically we need to find out how much is this equivalent static force. Okay, and this is nothing but in terms of this displacement, this applied force Wx that leads to the deformation U of x. Okay, so what we are going to say, instead of Wx, we are going to write this as basically Fs of s, which is the equivalent static force. So Fs of x is nothing but Eix times 2x, and again a double differential of that. Okay, this would be the equivalent static force that I need to apply. Of course, this is not the equation that I would be using. I'm going to simplify it further. Okay, and then write it in a form that is amenable for analysis. You can substitute the ux as x times zt, substitute it here so that you can get it as, sorry, not t here, this is x. Okay, this you will get it as phi x, and z you can take outside because z is a function of t and not x. Okay, now if you remember my omega n square, okay, what's happening? Omega n square. Okay, if you remember, omega n square is k equivalent by m equivalent. Okay, which is ei x phi x square divided by 0L, so integration over 0 to total length mx phi x square dx. Okay, so I can substitute this expression here. Okay, and I can find out what is the equivalent static force. and do some simplification. I'm not going to get much into that mathematics. You can look at the derivation. Just going to write down the final expression, which you get as omega n square times m of x, okay, times pi x, okay, times zt. And this is the expression that we would be using mostly. Okay, this is the equivalent static force that need to be applied on the structure to find out the internal forces and the moments. Okay. All right. So now we have the expression for the static force. What we simply need to do, apply this force to the structure and then see what is the internal force in the moments. But typically, as we have previously discussed, the time variation of response is not as important in earthquake engineering or design of a structure as much as the peak response. Okay, it is important, but what I'm saying that we can easily get the peak response using what? Using response spectra. So we have talked about the excitation due to ground motion, right? So we have said that our equation is this. Okay, this is our equation. Okay, this is the equation that I'm considering. So I know what is the response to this, right? Say a response spectra is given to me. Okay, now the response spectra is given for this equation, isn't it? There is no gamma term here. It is given for this. Remember, this is the equation that we have been solving in the previous chapter when we found out response of a single degree of freedom system subject to a ground motion. Okay, and the response spectra used to be given to us. So let us say this is the response spectra, something like this, where this is, let us say it is the pseudo acceleration, and this is the Tn. Okay, so I know that if a response spectra is given to me, I can find out the response for this system. However, the response that I need to find out is for this expression here. Now, because we are considering a linear system, okay, for this system, the responses are what? The peak pseudo acceleration is A, peak deformation is D and V. Okay. For this system, it would be nothing but the same quantities multiplied with this factor because it is a linear system. And this is some of the problems that you have done, isn't it? That response spectra is scaled to a peak ground acceleration of 0.25 g. Okay, something like that. So you initial, whatever the PGA is, you basically scale it to 0.25 g. So it is something similar to that. So what I'm saying, the response spectra is given for this expression. Now, for the generalized SDOF system, I need to find out the response to this, and it would be nothing but whatever the response to this SDOF system multiplied with this factor here. Okay, because that is the factor that is multiplied to excitation. So let us say it is A, D, and V, okay, as peak pseudo acceleration, peak displacement, and peak pseudo velocity. For the actual system that we are considering, the Z naught or this system here, Z naught would be this factor here times D. Okay. Is this point clear? Any doubt in this what I'm saying just right now? Anybody who did not understand what I'm trying to say here? Okay. If that is clear, I can also write this one. Remember, if the response vector is given in terms of pseudo acceleration, okay, I can write D as pseudo acceleration divided by omega n square. Okay, you can use either equation depending upon what response spectra is given to you, acceleration or displacement. Okay, so once the peak response in terms of or the peak value Z naught is known, I can find out what is the peak value of uxt, the maximum uxt, which I'm going to represent as u naught of x, okay, would be phi x times z naught. Okay, so I have found out what is the peak value of response in terms of time. So z naught, if I multiply this with the shape function, okay, so basically let us understand with respect to this beam here. Okay, it is like this at different instance of time. And at some instant of time, I know that Z0 is basically this. Okay, this is the peak response of Z. If I multiply this Z0 with the phi x, okay, which basically represents the shape of this, I can find out at any point the total deformation, total peak deformation as phi x times that Z0. Okay. So at each and every location, now I can find out what is the peak displacement would be. Okay.